Respected students, today we shall be discussing about continuity of functions. I told earlier, real world function means the value of the function or the image of the function is a real number for every argument. Of course, here we will be considering functions whose domain is also set of real numbers and codomain is also set of real numbers. So I usually refer them as real world functions. A real world function fx is continuous at x is equal to a if for every positive number epsilon greater than 0 there exists delta greater than 0 such that the modulus of fx minus f of a can be made less than epsilon whenever mod of x minus a is less than delta. You may compare this statement with the limit of a function. In case of a limit of a function, the limiting value L is any number, but here the limiting value L is nothing but the function value at the point x is equal to a. In other words, it is nothing but f of a. So what we say that a function is continuous at a point x is equal to a if the limiting value of fx is f of a. So again you can see that whenever we use the limit notation, there will be two types of limits. One is the left hand limit and another one is right hand limit. In other words, a function is continuous at x is equal to a if left hand limit is equal to right hand limit and it is equals to the value of the function at a. So we have to decide three values. One is the function value at the given point a, and another one is left hand limit at x is equal to a, and the third one is right hand limit at x is equal to a. So let us take one example and then we shall discuss. So take one example. As I told earlier, we were taking examples from polynomials. We are differentiated functions into two types. One is algebraic functions which contains polynomials and rational functions, and another one is algebraic functions which may contain exponential functions, trigonometric functions, logarithm functions, etc. So let us consider one algebraic function. Show that fx is equal to 3x squared plus 1 is continuous at x is equal to 1. Here the value of the function at x is equal to 1 is not given. So we shall calculate first the value of the function at x is equal to 1, and we see that f of 1 is equal to 3 into 1 its square plus 1. So we replace x by 1 and we get the value as 4. So f of 1 is equal to 4. Now if you take the limit of fx as x tends to 1, calculating both the left hand limit and right hand limit, you will see that it is equals to 4. So here the limiting value of the function is equal to value of the function at that point. So the function is continuous at x is equal to 1. In the second example, we will be considering a rational function. Let us take a given function as fx is equal to x square minus 9 divided by x minus 3 wherever x is not equals to 3, and f of 3 is equal to 6. It is given f of 3 is 6, it is given. So there is no need to calculate the value of the function at x is equal to 3 once again. We need only to test the continuity of the function at x is equal to 3. So let us write f of 3 is equal to 6 as the first equation. Now we will calculate the limit of the function. So here we will calculate both the left hand limit and right hand limit. So first we will consider the left hand limit x tending to 3 minus fx, which is equals to limit h tending to 0, we replace x by 3 minus h in fx. So I can write it as limit h tending to 0, 3 minus h plus 3. So this is equals to limit h tending to 0, 6 minus h, which is equal to 6. And similarly for the right hand limit, you may see that limit x tending to fx from the higher values of 3. Limit of the function fx as x tends to 3 from higher values of 3. It is equals to limit x tending to 3 plus, we split this x square minus 9 in the numerator as product of x plus 3 and x minus 3. And the denominator we retain x minus 3. So the common factor x